AI ecosystem partners. They help businesses run deep learning experiments at maximum speed and cost efficiency by optimizing, distributing, and managing your training workloads with their visualization software for AI infrastructure. And back in December, we held one of our Deep Learning Institute courses where Run AI delivered a presentation on how to simplify sharing GPUs in multi-GPU environments. Let's take a look at what they covered.
Hello everyone, and thank you for joining us. So today we're going to talk about simplifying sharing GPUs, and especially in multi-GPU environments. So a bit about me. I'm a programmer at Run AI. I'm the team lead of the GPU virtualization software. I put on some links to my social accounts, and I would be really happy to talk to any of you about anything that interests you, and nothing specifically in particular. So feel free to contact me, and let's just dive in. So we're going to speak about the challenges of using and sharing GPUs, and especially in multi-GPU environments. Now, GPUs are great. They allow us a lot of stuff in the fields of deep learning and machine learning, but they have some challenges in using them properly. And when I say using them properly, what I mean is not to write code in Python or something that uses them, but to manage them properly and efficiently, especially when we're speaking about a team with a few members and not just having a single person using a GPU alone. So the main issue with GPUs is that they are underutilized a lot. They are idle when we don't work, right? If I leave home, if I leave work for home at the evening, and I don't run anything on the GPU for the night, the GPUs stand idle for the entire night. And when I go for my weekend, they stand idle for a couple of days. They stand idle also during a work day. If I go to lunch or have a coffee break and I don't run anything in particular on the GPUs, they stand idle as well. Now, even if I'm working on the GPUs, but let's say I'm writing some code or developing a model. For example, when I use Jupyter Notebook, when I write these lines of code, the GPU stands idle because I'm not running anything on it at the moment. But the truth is that even when an application consumes the GPU and actually executes code on the GPU, like TensorFlow or PyTorch, then this application can have some tasks that are out of the GPU as well. For example, the application can do some I/O operations, like writing files and reading files, or writing to a network attached storage. Or it can do something on the CPU, like pre-processing the data and resizing images and stuff. So we can clearly see that GPUs are underutilized in a lot of time resolutions, and we would like to fix that and use them more in a better way. Another thing is that GPUs are too big. Every year, GPUs get more and more memory. They get more compute power, they get better, they get more advanced. But this memory might not be necessary all the time. Because, for example, when I develop a model and I use small hyperparameters, such as batch size or the number of layers, then this means that my model, while being developed, consumes not so much GPU memory and small amounts of it. And even if we speak about models and not just developing a model, there are plenty of models that will not use the entire GPU memory. if we're speaking, for example, of a GPU NVIDIA V100 that it's got 32 gigabytes of memory, then I have plenty of models in mind that do not require these amounts of memory. Now, as GPUs get larger and better and more advanced, and especially in terms of memory, it's getting harder and harder to utilize them properly. And as said in Spider-Man, with great power comes great responsibility. As GPUs getting better, it's harder to use them properly. Now, at the same time, GPUs are also too small. GPU memory is expensive in comparison to CPU memory, as we call it, RAM. We're used to that you can expand the amounts of CPU memory, but increasing GPU memory is not possible because GPUs come with a fixed amount of memory. So the only thing you can do is purchase a new and more advanced and a GPU with more GPU memory, with more memory. But it's not infinite because, for example, advanced GPUs have 32 gigabytes of memory and maybe they will get bigger, but it's not like in the CPU fields when you have hundreds and hundreds of gigabytes of memory. Now, in addition to that, applications that use GPUs, they consume a lot of memory. In opposed to CPU applications, where we are used to applications that use several megabytes and maybe several hundreds of megabytes, when an application uses the GPUs, when an application uses a GPU, then only creating a context for being able to use the GPU requires several hundreds of megabytes of memory. And it's very rare and even impossible to see a GPU application that consumes a few megabytes or a few dozens of megabytes. All that means that only a few applications can run on a single GPU simultaneously, because each one of them requires a lot of GPU memory, and we have small amounts of it. Now, teams that want to run more GPU applications or run the same applications but consume more GPU memory, for example, increase the batch size, increase the image size, they need to spend a lot of money in order to purchase more GPUs. Now, sharing a GPU is hard. And when I mean share, I mean sharing it between a few applications and between a few users and team members. And why is that? Because applications that run on the very same GPU share its memory. Every single byte of memory that is allocated by a single application is taken from another application to allocate. They share the same amount of memory in total. This means that the only way for multiple applications to share a GPU is to cooperate with one another. Every single application should know exactly how much memory it should allocate and to not exceed this amount of memory. Because if an application exceeds its amount of memory that it should allocate, then it's taken from another application that should have been able to allocate its requirement. In addition to that, many applications, for example, TensorFlow, they assume to run solely on the GPU. It is very common and it's have some advantages, and therefore this is the good practice and this is what's recommended out there. But this means that code changes are required from users and data scientists in order to modify the application to allocate only a portion of the GPU memory and not the entire of it. And sometimes it's even impossible to do because, for example, if you get a Docker image with an application inside of it and you're not accessible to its source code, then it might be impossible for you to modify the application in order to allocate only a portion of the GPU memory if you want to run it simultaneously along another application on the same GPU. Now, if we're speaking about multiple users that want to share a GPU in opposed to multiple applications, this means that this makes stuff a logistical issue as well, because users should coordinate and decide how much memory should each one get and should each one allocate. And they should make the decision together, and everyone should know their amount of memory that they're allowed to allocate. Now, sharing a GPU in a dynamic way is harder, and let's see what dynamic means. If, for example, we're speaking about single users or even maybe small teams, so they can have a static policy. For example, if I am a member of a team of 3 members, then we can decide that each one of us gets a third of the GPU memory. It's easy and it makes sense, but this means that GPU memory will be kept unused many times because if, for example, I'm not working at a specific day, or if I'm coming to work a bit later, then I will not use my third of the GPU memory. And this unused GPU memory could have been used by another team member. The other team member could, for example, run more GPU applications, meaning run more deep learning models, or consume more GPU memory. For example, running larger models or increasing the hyperparameters, the batch size, the image size, the number of hidden layers. So in addition to that, sharing a GPU in a fair way is also hard. And this is because we want to share GPU equally between users and not applications. Users should not be granted more GPU memory for running more processes and more applications. If I'm working in a team, then each one of us should get the same amounts of GPU resources as anybody else. And it doesn't matter how many processes and how many applications I run, I should be able to consume the very same amounts of GPU resources, just like my other team members, my colleagues. But that's not the case, because GPU execute commands from different applications equally. GPUs are not aware of people and of users and, for example, of projects and teams and priorities. All they see is processes, is applications, and the GPUs are being shared equally between those applications and processes, which is not what we desire. All right, so until now, we talked about sharing a single GPU. Now, sharing multiple GPUs is much harder. And why is that? It could happen on a multi-GPU node, a single machine, or even a cluster of nodes of multiple machines. And this is because suboptimal decisions can cause fragmentation in free GPU memory. Applications can run on different GPUs and leave some amounts of free memory in each of these GPUs. But then the next application that will require some amount of GPU memory could not find a single GPU with the desired amount of GPU memory to be free, because each one of the previous applications were executed because of a bad decision-making process on a different GPU. And this keeps memory fragmentation across the node or the cluster itself. Now, this happens because containers and processes and applications are assigned to a single GPU for its entire life. When I run an application and a process is being executed, then for its entire life, it uses the very same GPU. But the cluster and the node is a very dynamic thing because jobs start and end in different times. And I find this image a very good example because you can see the man reading the book as if it's an application that's using a GPU. And it might use the very same GPU for a few hours and a few days and even a few weeks. But the train is moving in the background, and the cluster and the node is a dynamic thing, but the application is not aware of it. And this creates a gap between the static application and the dynamic environment in which the application is running. And how Run AI can come to the rescue and help with all that? So first of all, we have our cluster orchestrator. We already saw that managing jobs from different users and projects and teams is extremely difficult. And this is because GPUs and the software that comes with GPUs is not aware of these terms. It's only aware of processes and applications. And it's extremely difficult to do in a multi-node cluster, where there are plenty of GPUs of various types and of various sizes. Now, we at Run AI have complicated Kubernetes components that are responsible for exactly that, for deciding when and where should each job run. Our cluster orchestrator looks at the cluster itself and at the node, at every single GPU in the cluster, and makes the optimal decision in terms of where a job should run. Because each job requires different GPU resources, different compute power, different amounts of GPU memory. And this decision making is a very hard thing to do. We have scheduling algorithms and complicated components that are responsible for exactly that. So the users don't have to decide themselves, and we provide the best decision making in order to efficiently use the entire cluster and each and every one of the GPUs in it. Additionally, we have GPU virtualization. We provide software that allows containers to use a fractional GPU, meaning the application will be exposed to only a portion of GPU memory. Now, this allows sharing a GPU between containers and applications really easily. And why is that? Because first of all, this eliminates the necessity of code changes in the application itself, because the application is exposed to a smaller virtual GPU. So even if an application allocates the entire GPU, it allocates the entire virtual GPU, which is smaller than the actual physical GPU. Now, Additionally, it allows enforcing GPU memory consumption between applications and providing and assuring that any application will not exceed its limits and overwrite another application's memory. If we'll take this diagram as an example, we can see that a user can submit 3 commands and 3 jobs, and each one of them asks for a half of a physical GPU, meaning a virtual GPU with half of the memory. And we can see that the 3 containers are now being run on 2 GPUs, but 2 of the containers share the same GPU, which is GPU number 1, and GPU number 2 is executing the 3rd container on half of it, but another half of its memory is still available for future containers and jobs to come and use it. So to sum it all up, we saw that GPUs are too often underutilized. We saw that sharing them properly is hard, but sharing them in a multi-GPU environment is much harder. And the decision-making process has some real serious implications and consequences. This makes the decision-making process be more important when we speak of multi-GPU environments. Okay, so thank you all for listening and joining us. Again, my name is Raz. I will be really happy to talk to any of you. I will be happy to answer any questions, either now or later, so feel free to contact me. And thank you again.
Many thanks to our friends at Run AI, and our next live online DLI course covering the fundamentals of deep learning is on March the 25th. And we're pleased to say that Run AI will be our guest speakers. To register for the course at a discounted price, please click the link in the description and scan. And now happy to announce that we're offering a guided proof of concept in collaboration with Run AI. So you can now see firsthand how Run AI's virtualization software will allow you to gain greater control and visibility of your AI infrastructure. To find out more about the POC offerings that Scan and Run AI are offering, please click on the link in the description or get in touch with the Scan AI team.